aspect, polarizing the solvent matrix. Even so, within that scope, the wish list is huge. We want high NMR enhancement in a predictable way. That's important, at high magnetic fields, at high magic angle spinning frequency, at a wide range of temperature, ideally above the protein dynamical transition, but that's going to be hard. Rapid buildup for sensitivity, and low microwave power does have a distinct benefit of then being more accessible to many researchers, being able to access a larger sample volume. And finally, polarizing agent that you can choose, pick and choose, so that it's compatible with the sample of interest. There, in all of this area, there is room for improvement. So the key to this, in fact, lies in, and I'll give you examples for that, in understanding the intricacies of electron spin dynamics and coupling. For example, specifically, how many coupled electron spins are contributing to flipping a nuclear spin? What is the mechanism by which the electron spins generate the energy of the order of the nuclear alarm frequency? So for example, just as an example, if you take the G anisotropy, where a different orientation of E1 and E2 of a nitroxide is responsible for providing that energy difference of the nuclear alarm frequency. Even if you take that case, still one needs to consider the transition probability. So according to Landau-Zener model, if you take that, to have efficient transfer, loss as minimally as possible, lossless transfer, you need a high perturbation E1, and it inversely scale with the energy crossing rate. Okay, so high perturbation can come in the form of some form of dipolar coupling and J coupling, and I'll be talking about that a little bit, as well as the number of electron spins coupled. To have low energy crossing rate, to have high adiabaticity, one can have that with a low G anisotropy, slow magic angle spinning, or lower B0, because that'll squeeze the energy. Of course, slow MAS and low B0 is not the solution we want. So then one can consider, can we do something with narrow line, low G anisotropy radical, narrow line radical, if there's a mechanism to shift the frequency of the second radical by the NMR frequency. So I'll be giving you an example where that kind of construct can be done and could be very exciting. So to orient ourselves, let me briefly just mention the 4 categories of DNP mechanisms. The Overhauser effect requires hyperfine fluctuation of the order of the EPR frequency. It's mostly used in solution state, and in solid state, one would need to have the source of the fluctuation in the sub-terahertz regime, and the source of that experimental is actually not clear yet. So this is maybe a discussion for another time. Solid effect is not very efficient, but very exciting if one has high microwave power. Ideally, in fact, pulse DNP, that's what's so exciting, to be able to do coherent resonance transfer. That's of course what will transform DNP, what Bob and Zanders and many people, including us, are dreaming about. So that will be transformative, but that would require an entirely different kind of hardware. So with the current hardware, cross-effect and thermal mixing rely on allowed transition, but even there is a huge amount of improvement and tuning that we can do. So those are the 2 mechanisms I want to talk about. In cross-effect, specifically, the role of dipolar and J coupling is a key point that I will discuss. And in thermal mixing, it's clear that many electron spins need to be involved, but how exactly the spatial distribution of the involved spins become important. So those are the 2 topics that I will discuss. So to figure out the dynamics, the mechanism, and the mechanism is key so that we can improve the performance, I'll list them. One can measure, we measure DNP enhancement as a function of frequency, power, and buildup. Those give us key clues. We can measure CWP line shape. but almost more exciting capabilities if we can do echo-detected EPR, because that gives us ideas about the heterogeneity, the nature of the line broadening and relaxation. The relaxation time itself can be directly measured, as well as pump probe experiment. Those are very exciting experiments, especially Daniela Goldfarb and Shimon Vega have used this, pioneered this approach for many years. And we too are really taking advantage of pump that simulates DNP and probe to detect what the spins are up to. And finally, AWG pulse shaping is a really key tool for both EPR and DNP. So those are the diagnostic tools that I'll be in part using. So let's start with the cross effect. I just put this slide up to remind you what do we need for cross effect to work. We have 3 ingredients. First, the cross effect energy matching needs to be fulfilled. The E1 and E2 frequency differential matching the NMR frequency. Second, we need coupling for the transition to be probable. But that is what the spins are doing, not what the microwave is doing. And third, what the microwave is doing now is generating a electron spin polarization potential. So you saturate, you need an inhomogeneously broadened line to have a polarization potential to maximize the delta P between E1 and E2 population that generates enhancement. So let me focus briefly on aspect 3, the polarization, shape of the polarization. This is in part already published data, but I do that to orient ourselves. So Ilya Kaminka has pioneered this AWG or implemented this in our lab under static condition. You can, of course, using broadband saturation, really maximize that shape to have the maximum polarization differential. But that was under static condition. You have a maximum at a certain chirp width, and then it goes down again because at some point you're just saturating the entire line and the benefit goes away. But under magic angle spinning, the chirp over a nitroxide radical wasn't beneficial. And that's because you have a line that has a G anisotropy spanning the entire frequency range that encompasses E1 and E2 that we need to keep up the polarization differential. And on magic angle spinning, you're pretty much hitting all frequencies and smearing out the needed polarization differential. So in subsequent study, Asif, Equbal, and Tagami have shown that you can remedy that when you utilize this mixed narrow broad radicals that so many of those here in the audience have developed and pioneered. If you have a mixed radical, now you can contain the polarization such that you can put the microwave on, for example, the tridal radical, and on the magic angle spinning, still you're only saturating this portion. And so this has then a saturated polarization, and the other spin, for example, of the nitroxide can provide the not saturated polarization and gives you that benefit. Then really broadband excitation can dramatically enhance the DNP enhancement under magic angle spinning. You can then further go ahead and customize your shape to that of the EPR line width, as well as in the future customized by the relaxation of the electron spin. So really neat games can be played. So this was just about controlling the shape of the polarization gradient. A second aspect, which is a bit more delicate to explain, but a very important one, is the timing. Plotted here is a rotor period. This is simulation done by Dr. Asif Equbal. In a rotor period, the excitation of microwave transition and a cross effect event are separated in time. If you have a fast relaxing electron spin, in that between that time, the polarization will have decayed, the one that you were trying to hold down if you have CW, monochromatic CW radiation. So if you have a broadband AWG type of setup, then you can hold the spins down and therefore really even under fast T1 condition, keep the polarization differential between E1 and E2 and therefore maximize the transfer. So this is beyond just the shape, it's also optimizing the timing. But the third aspect is also very important. Even if you have all of that down, you still need to maximize coupling. So that's when J coupling comes in. One half of the next slide is published, the other half is unpublished. So in a very recent paper by Tagami and Asif Equbal, we have shown that J coupling, and others have shown too, this paper in addition illustrates that J coupling is very important. You take various orientation of the radical, and generally, even though the orientation do matter, if you have a threshold J coupling, you have for most orientation a much greater enhancement. But even more importantly, under magic angle spinning, if you go especially to higher spinning rate, you need that J coupling that's rotationally invariant to keep the enhancement and not lose them as you start spinning your sample. Now, if you have someone as smart and observant as Dr. Equbal, you wonder about this dip. You don't just take this for granted and think about why is it going down? Is this real? It's going up here, but is that dip real? And that generated a really exciting piece of work that I will share. That it's not just that you need J coupling, the balance has to be right. You need J coupling that exceeds a certain value relative to the dipolar coupling. For example, a ratio of J over D of 0.7 can be detrimental. Most of the orientation give you zero enhancement. You need J over D of 1 and higher to have higher enhancement. So why is that? I don't want to go into too much detail, but I can illustrate the idea here. You have your Page pattern of dipolar coupling that goes from minus D half to plus D half. J coupling shifts that, but if you shift it by not enough, then you have your highest intensity as zero effective coupling. So that can kill polarization, and you need to go further. Now, interestingly, many radicals that we are working with in DNP falls actually in that range. So that can explain a lot of aspects. There's a huge amount of improvement and opportunities that one can exploit. So I write here, maximizing transition probability by an optimal balance between D and J coupling. I should really say that. If you have high coupling, then not only do we benefit from high field, but high spinning frequency. You see, if you have J over D exceeds a certain range, then you have very high enhancement consistently over a range of spinning rates. So, but I wanted to share with you another aspect that's really surprised us. So I said in the beginning, you need high perturbation, role of D and J coupling, that's what I covered. How about many electron spins? That was another aspect, but how about tuning this crossing rate? Can we make that smaller? Because that's also key to performance at high field and fast magic angle spinning and so on. So can we engage more electron spins? And can we utilize narrow line radicals to our benefit? So that's where the thermal mixing idea comes in. Of course, this has been around in the literature for a long time, and it's highly debated right now as we speak. But let me share you an observation that we didn't intend to have, but we were surprised ourselves. So the question is, can narrow line radicals punch above their weights? What do I mean with that? So you take a tridal radical, OXO 63, what are soluble. Under our condition, it has a line with about 65 megahertz. So can it use to polarize effectively proton NMR? Well, proton NMR at 7 Tesla, you need you need 300 megahertz. The line with itself doesn't offer that. Except for a solid effect that you see at 10 millimolar tridal, you see the solid effect that is there, but not very high, something like 10-fold. But as so you see the center resonance. Actually, many people have seen it. We went back to the other published paper and see this effect. You go to 20 millimolar, this thing grows. You go to 40 millimolar, these things become bigger. You go to 100 millimolar in water glycerol, it's huge. It's only the central peak. What is this? Is this the Overhauser effect? Is it a thermal mixing effect? Well, it is not the truncated cross effect. I can tell you that, at least by the way we have defined truncated cross effect, which we have introduced a while ago. when you have one radical and another invisible radical that's broadened, but that comes from the G factor from a different radical type. So we don't have here any other radical other than tridal, so I just cross it out here. So what effect is it? We can get some clues. First of all, by the shape, it's clearly dispersive. That's one. The other aspect is 20 Kelvin to 120 Kelvin, all the way. 20 Kelvin, 30, 60, 120 Kelvin. The effect is there across this wide temperature range. And at higher temperature, it becomes a little bit more probable, the central peak. So in fact, dispersive and minimally temperature dependent isn't consistent with the Overhauser effect mechanism. So we believe it's a thermal mixing mechanism. So let's go with thermal mixing and prove to ourselves that this is indeed what we have. Knowing that is important, because if you know it's a thermal mixing effect, then you do something different to the radical to optimize it. If you know it's an Overhauser effect, you look to other parameters to optimize. So knowing the mechanism is key for the next step. So thermal mixing requires, first of all, many electron spin coupling. I just quote, for example, a recent paper by Wenkebach that showed cross effect and thermal mixing, two sides of the same coin, or two distinct limits of the same process. Fundamentally, you have still a triple flip process, or at least that's a foundation. In cross effect, you rely on recoupling, and the energy difference comes from the G anisotropy typically. And for the thermal mixing, the coupling is strong. Okay. And so I add to that this cartoon that I keep showing. This is what we thought long and hard about and drew this cartoon. You need coupled electron spin that are very strongly coupled, but you also need another electron, for example, an isolated electron spin that then has the frequency difference that corresponds to a nuclear alarm frequency. So dipolar coupling has to be very strong. Dipolar or J coupling, in fact, has to be very strong to encompass the NMR frequency. Now that means you need clustering. Luckily, there are some really exciting paper by Van Dorslab and Pons, as well as Mike Bowman, that prove tridal under many different conditions cluster. Not only the Finland tridal, but also the Oxford tridal, and dimer, trimer, all the way to nanoparticles. So we know from the literature, tridal can readily cluster. So next, do clustered radicals then offer sufficient broadening to account for E1 and E2 to encompass the NMR Lama frequency? Well, simulated data by Asif, Equbal show indeed, if you have an EE distance of the order of 6 angstrom, for example, which can be easily seen if you have strongly clustered spins, you have 300 megahertz. And by having different ratio of the strongly coupled 200 megahertz, weakly coupled 15 megahertz, you in fact can have broadening of that order of magnitude and can play with the proportions. Experimentally, I'll tell you a caveat for some technical reason. We just did that at X-band, so you cannot take the absolute frequency too seriously, but we see going tridal from 1 to 100 millimolar, you see dramatic broadening. This is at least something of the order of 100 megahertz. So that kind of broadening can be indeed directly seen. Now, that's not enough. As I was showing with this cartoon again and again, we need an asymmetry in the electron spin coupling to drive thermal mixing DNP. And I want to point out, because we really like this paper, when we look through the literature and trying to figure out, we found this nice paper that we hadn't seen before from Walter Kirchenberger from 2016, PCCP. And they did quantum mechanical simulation and offered some microscopic insight how the spins have to be distributed to give thermal mixing DNP, and they predicted that you need a strong asymmetry in the electron-electron coupling. They in fact have seen thermal mixing DNP with tridal in certain other tridal in THF toluene. They predicted that tridal oxo 63 wouldn't give thermal mixing DNP, which we see. However, the framework is there, and we very much agree with that framework of their paper. So let's look at the EPR. So 10 millimolar, you see echo-detected EPR, a certain shape. 40 millimolar, where we start to see the central peak really grow. We see an asymmetry at 100 millimolar, it's completely obvious. So this means you have an inhomogeneously broadened line, you have multiple population, at least two population of spins. And we would like to think that those are, at the very least, some population of strongly coupled, some population of isolated electron spins of the triidal radical. So finally, what do we need to then really prove, right? Because the debate in the literature is very heavy, we need to prove it. What do we need to prove to know it's thermal mixing? And so that is showing that you have a hyperpolarization of a subset of electron spin. Again, I show nice quantum mechanical theoretical simulation by Kundu and Vega. And in fact, they quote 72 Atsakin paper, which I read briefly and predicted something along those lines. You need hyperpolarization of electron spin population, and Vega and co-workers have shown, for example, how the EP alignments would look like when you have thermal mixing effect. This would be the green one, okay? You kind of see the type of EPS spectrum that I've shown just before. And the Eldor profile show you this hump up. You have, you excite, but you see an enhanced intensity. This is hyperpolarized electron spin. Can we see that? So this was the final nail that we needed to prove it. We have seen, this is experimental data. This is one of the most exciting data that I've seen, I would say. Experimental Eldor data. See 10 millimolar triidal, where there was not much effect of the thermal mixing, 40 millimolar triidal. Now you see this huge hyperpolarization of electron spin. You saturate at this frequency, it's a pump probe experiment, and your probe electron spin tells you it's now higher polarized. Right, so this is the final proof that you have hyperpolarization, okay? So this is really exciting. Now, why do we care about thermal mixing DNP? Well, there is a lot of potential. First of all, it has a very low microwave power requirement. For example, compared to solid effect anyway, you need relatively little power, 200 milliwatt, to saturate the effect entirely. That's exciting. The build-up time would be very rapid, except in this kind of sample, spectral diffusion is rate limiting, and therefore the build-up of thermal mixing pretty much is the T1 of the proton. So that's nice, at least it's not slower, but it can't kind of surpass that. But now that we know the mechanism, that there's a lot we can do. So I show you here enhancement at different concentration. 100 millimolar gives you a solid effect of only factor of 2, but a thermal mixing of 110. Now that factor is good. It's very exciting that we can get that kind of high enhancement, but it's not so much that I'm suggesting 100 millimolar trial is the way to go. I'm just showing you a design principle. Once we know this can be done, of course it would be better one can shape the spatial distribution of trial to really take advantage of it, okay? So, oh, this was just published yesterday. So it's, I hope that many of you haven't seen it yet. So you are maybe at least a little bit surprised. So take home message one, there's huge potential to improve DNP performance, especially if you can understand better spin dynamics. In thermal mixing DNP, I've shown you a wide range of temperature and low microwave power requirement. I haven't talked about B0 and MAS frequency dependence, but in fact, I know there's a lot to gain here. You have strongly coupled system that really should be something that we can prove in the future and show in the future. And sample compatible polarizing agent. Once we know what the design principle is, other kinds of polarizing agent can be developed. Second, I did show you the balance between J coupling and dipolar coupling is very important. And that is really also what made high magnetic field and high magic angle spinning DNP very probable. So, and in fact, both conditions can be combined. So there is exciting development ahead of us. Take home two, all of this did require diagnostic. So it's very important for us to figure this out, the ability to detect and manipulate electron spin, polarization and dynamics, that is key. And in fact, that slide is a perfect opportunity for me to acknowledge past and present member. The current idea drivers are Dr. Asif Equbal, who did most of the work that, the computational work that I've shown, Miranda Lee and Kan Tagami, who are really wizards of experiment, Dr. Sheetal Jain, who is a project and idea driver for actually another kind of DNP where he is really focusing on the local hyperfine DNP. and former students and trailblazers, Dr. Ilya Kaminker, who really set this whole setup up initially, Alisa Leafsley, Alicia Lund, Tingan played a very important role. And initially, Brandon was brave enough to start the very first version. So with that, thank you for your attention.
All right. Thank you, Songi, for your very interesting presentation and also your generosity in showing us all the latest and unpublished results. I think that's very interesting. And also, like, maybe one of the perks of being like a host is also like, I can ask a question first before anyone else. So maybe I'm just curious. So like, if you use 100 millimolar like radical concentration, what do you expect on, like, would it cause anything like bleaching or depolarization, like what you will see in a cross effect? I'm not sure if you do this on static or cross effect.
Yeah. So that is why it wasn't so obvious that having 100 millimolar triidal would do anything good, right? If you have a homogeneously broadened line, let's say you take, let's just take a strongly coupled, completely homogeneously coupled electron spin system. If you saturate it, you would just saturate, you would just bleach them. There'll be no DNP effect. So you do need the asymmetry, the spatial, you need a presence of the strongly coupled and the weakly coupled system at the same time for this to work. So for triidal, we just got lucky that triidal seems to cluster partially, stays isolated, partially clustered. So that was the key. And now the next step is how can one design that on purpose to generate such systems?
So I'm just wondering, like, so if you just like prepare the same sample without the radicals, I mean, just purely diamagnetic, would it, do you see anything like a loss of a signal without microwave?
Yeah. No, of course, you do see that, but it's not as bad as you think, probably because there's clustering. Not all nuclear spin see all the radicals. So there's big pockets of nuclear spin that are not seeing the radical. And 55 molar is still way more than 100 millimolar radical. So it's broadened, but not as bad as you'd think.
Okay.
So there are several questions. Fred Mentic asked, would you expect to see thermal mixing under magic angle spinning conditions?
Yeah, that's a really, really good question. So Asif and I knew that this question will come, so we thought about it a bit. In this particular case, you notice the dispersive pattern. So if you're under magic angle spinning, it might just zero out. But now comes the part. We are very confident, and we have seen it with other narrow line radicals. You can actually tune the shape of the dispersive pattern, and now comes the part that's now, again, I'm just gonna spill the beans. Depending on the role of J and D coupling, you can, dipolar coupling, you can change the dispersive to absorptive. And if you do, absolutely, you can see it under magic angle spinning.
Yeah. Bob, you can comment, like, actually, we also saw this a lot in the past literature where you have the dispersive line shape in the middle of the, right, Bob? Can you comment on that?
Colin Hugh was the first person, I think, to record that dispersive line shape, probably about 2006. And we never really understood it. We studied it in some detail. Cody Kahn looked at it in great detail, but we've never really understood it. Now, we never went to, we've been working at 15 and 20 millimolar. We've never, I don't think, ever gone to 100 millimolar or 50 millimolar even, for fear of bleaching.
That's right. We actually went there because we were suspecting clustering, and we saw these nice papers about clustering. So we wanted to on purpose generate clustering. So that's how it came about.
So there's a question, you've done all this with OX63, which you see it with Finland. Finland radical, which is just the methyl groups. I'm not sure it clusters as much, or maybe it's.
Oh, that has been shown nicely by Walter Kirchenberger. So we had this idea, and then we looked in the literature because we knew that thermal mixing is a big debate. And then we actually were surprised that we haven't seen his paper. But his paper actually shows thermal mixing with the Finland radical and puts the whole theoretical framework right there. He does predict OXO63 won't work. So we did have at least something surprising. But yes, Finland radical will absolutely show thermal mixing DNP.
And there's a final question from Thomas Schmidt. Do you think adding dysprosium to change the T1 of the radical and approaching a lower temperature at 5K It doesn't say what he's, okay. Did you think about adding, sorry, did you think about adding dopants? Yeah.
Like gadolinium, I think.
Gadolinium, okay.
Exactly, this is common in the, yeah.
Right, I will, depends on whether you mean a static or MAS. On the static condition, you know, there could be two effects. On the static condition, simply you can pulse faster. That would be one effect, but that doesn't explain actually the huge enhancement you see. The other effect could be, and I'm now going to speculate, okay, is gadolinium does offer spin density that can help flip-flop with invisible population relative to radicals. That could be one effect on the static effect. On the magic angle spinning, it's different. On the magic angle spinning, there's a balance between a high and low T1. Too fast T1E is not good because you will basically lose the polarization over the rotor period and you will not be able to benefit from the transition. But too slow T1E definitely generates depolarization because you want the polarization to replenish by the next rotor period. So I can imagine that you have to, once you know exactly how you have to tune it, that with this gadolinium or other radical that you could tune the T1E.
So there's another interesting question. Have you tried this with BDPA? For example, BDPA dispersed in OTP.
Yeah, yeah.
Does that show this? Does this
yeah,
show?
so this is now spilling the beans. That's like conference style, right? Yes, and Bob, you'll be very interested in this. I am pretty sure we have thermal mixing in BDPA too.
Mm-hmm.
So that's the interesting part. That's the interesting part because you do need to see now a different shape, right? Because we of course know that the BDPA effect with the Overhauser-like effect was very effective at high magnetic field. And magic angle spinning, you need an absorptive peak. So if we can tune it to be absorptive, and it looks like we can, then this would be thermal mixing. That would be my view. Now I spilled the beans.
Okay, there are a bunch of other questions. We're well over our time limit, about 30 minutes. So Songi, maybe you could look at these other questions and answer them, and they're available in the Q&A portion of the Zoom program.
So how do I answer then? Do I just stay on and answer in person, or do I just type in?
You can type the answer here, or maybe I will ask the participants if you're interested, send Songi an email. That's the easiest way.
Okay.
Yeah.
Okay. All right. So as I said, we're about 30 minutes over, and I can see the number of people watching us has decreased by about 25 or 30 individuals. So we'll have another one of these next week. It will start at 11 a.m. Central Time. That's 8 a.m. California time and 5 p.m. in Europe. And the speakers next week, I believe, are Jeffrey Bodenhausen from the École Normale in Paris, and then Mikhail Leskas from the Weizmann Institute in Rehovot. Yeah, and one other thing, I was just reminded by Michael Mardini to please answer the polling questions. Are there polling questions? Yes. I don't see them, but Kong, how about the polling questions?
It's there. I mean, I have a lot of yep, they're answering it. I can see it now. Like, can you not see it? Like,
Yeah.
It should pop up.
Yeah, it's popped up. Okay?
Exactly.
Okay, so the polling questions: do you prefer one speaker, 1 hour, two speakers, 30 minutes? And did you subscribe to the mailing list? Okay.
You should. Everyone should.
And there's a third question. Do you prefer the standard Zoom format without, where all participants can see each other, but without the Q&A function, or the current webinar format that we have? Okay. We've had people saying that they would like the webinar. We've had other people say they would like the meeting. So we're still trying to tune this whole experience to optimize it for everyone, and as I said, keep the participation up. So one other thing I'd like to mention just before we sign off here is that we do want to get postdocs and students involved in these presentations. And so could if you're a postdoc or a student, or if a principal investigator has a postdoc or student, they would like to do one of the presentations, then would you please send a brief abstract to Kong and to myself, so we know what you're probably going to speak on. And then sometime in the future, we're going to start adding students and postdocs as soon as we have a sufficient number of good talks available. Okay, so with that, I would like to thank everybody for showing up today. We really appreciate it. And as I said, next week we'll have another one of these, and Jeffrey Bodenhausen and Mikhail Lester will be here to educate us in the recherche aspects of maybe low temperature deuterium NMR and DNP applied to materials. So thank you again, and we hope to see you in about a week.
Okay, I just end the poll, and then I would share the results. And then I just keep reminding, I know I've been saying it many times, sign up the mailing list, and then check the recordings, and students and postdocs do submit your abstract on using the online submission form on our group website, So thank you and see you next week. All right, bye.